Today we're looking at section 2.5, proving statements about segments and angles. Our essential question, how can you prove a mathematical statement? So here we get into geometric proofs. So a proof is a logical argument that shows a statement is true. There's different types of proofs. Most of the proofs that we will be looking at are what are called two-column proofs. Okay? It's numbered statements and corresponding reasons that show the argument in a logical order. The reasons we can use in a proof are postulates, definitions, properties, and theorems. We can also use given, which we looked at in the last section. Okay, so we can use given information as well. Then we have congruence of segments theorem and congruence of angles theorem. Okay? But these are, again, our reflexive, symmetric, and transitive properties that we talked about in 2.4. So the only thing that changes is what we're referencing. So congruent of segments theorem, reflexive property, AB is congruent to AB. That's saying those two statements are the same thing. Symmetric, again, I can switch where it is on the equal sign. So if AB is congruent to CD, then CD is congruent to AB. Transitive, if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. So I can do that with congruence of our segments. I can also do that with congruence of angles. So reflexive property, angle A is congruent to itself, angle A. Symmetric, angle A is congruent to angle B. So I can flip that, angle B is congruent to angle A. Transitive, angle A is congruent to angle B is congruent to angle C. So angle C, A and angle C must be congruent. Okay. Again, I'm going to reference those as reflexive, symmetric, and transitive. We won't specify that we're looking at congruence or we're looking at segments or angles. Okay, but this lets us add those in. So then example 1, we get into a geometric proof here. Okay. And most of the statements are here for us. They have a couple things for us to fill in. But basically it is there for us. Here I have given information. Okay, and here I have a picture that goes along with that. And the picture may have given information as well. In this case, the 2 is congruent to 3, which already matches, which is here. So they say angle AXC is congruent to angle AXD. That is that second part of my given. Now, different people have different thoughts on this. If I was doing this on my own, I would also put 2 and 3 up here. They didn't do that in this proof because they're waiting till they're going to use it. So if you notice that everything is not given to you, everything in the given is not listed at the beginning, look for other places that pops up. Okay. So then I have 2 and what I'm trying to prove is that 1 is congruent to 4. So I'm starting with letters here. So I want to somehow get, and even here I only have 2 and 3. I somehow want to get angles 1 and 4 into my statement. So if I look at AXD, right? AXD is made up of angle 2 and angle 1. So angle AXD is equal to the measure of 2 plus the measure of 1. Okay, and the order of those don't really matter. That is our angle addition postulate. Okay, if I add 2 smaller angles, I get the larger angle. And I'm going to change how I write this. I'm going to write 1 and 2. It'll be less confusing for most people. Then AXC is here. That's 3 and 4. So the measure of angle 3 plus the measure of angle 4. Again, angle addition postulate. Now, I have my 1 and my 4 that I want. The problem is I want them on opposite sides. So, but AXC and AXD are equal, and AXD is equal to this, AXC is equal to this. So I can say angle 1 plus angle 2 is equal to AXD, which is equal to AXC, which is equal to angle 3 plus angle 4. So that is our transitive property. And that lets us get it on our 2 sides. Now, the only thing that's the problem is 2 and 3 are in here, and I don't want 2 and 3. So 5 says measure of angle 2 equals a measure of angle 3. I know that because it's given. Six then says they change this to angle 3 by substitution, since that's equal. I would be fine with skipping that step, and I say to get here, I want to get rid of this, so I'm going to subtract the 3 from both sides, and that is subtraction. Okay. It depends on how picky you're being. I would be okay with saying, all right, we're subtracting this statement from this. These two things are equal. So I'm okay with calling that the subtraction property, but that's not what they did here. So then we flip it over, example 2. We have another fill in the blank proof. Okay. Step 3, I'm going to skip what they would normally do here for step 3. We'll come to this later in a place that we can't really avoid it. But it's something that our book likes that I'm not a big fan of. So we're given that BD bisects angle ABC. We're trying to prove that angle ABC is equal to 2 times the measure of angle 1. So I start with my given, BD bisects angle ABC. Okay. Whenever you have a keyword in your given, you want to think about what that keyword means. So bisects means it cuts it into 2 equal parts. So what 2 equal parts do I have here? I have angle 1 and I have angle 2. So I'm going to say the measure of angle 1 is equal to the measure of angle 2. And that is the definition of an angle bisector. All right, so when you have that keyword in there, look at what that keyword means. That's probably going to be one of your next steps right after the given. Then it says angle 1 plus angle 2 is equal to ABC. The measure of angle 1 plus the measure of angle 2 is equal to the measure of angle ABC. Okay. That again is our angle addition postulate. We're saying those 2 smaller things add up to that 1 large thing. Now what I want is I want 2 measure of angle 1s equal to ABC. But I know 1 and 2 are equal. So I can sub angle 1 in here by substitution property. And then I have that the measure of angle ABC is equal to 2 times the measure of angle 1. Now, technically, if I'm getting picky to make this match, I use 2 things here. Right? I used the symmetric property, and then combining measure plus 1 plus measure plus 1, I simplified. So I'm going to put both here. I'm going to say symmetric, which let me switch it, and simplifying. Again, it's not addition, because addition says I add the same thing to both sides. So the addition property is not when I'm combining like terms. I would take combining like terms instead of simplifying, but I prefer simplify. Okay. Then example 3, right, they leave blank for us. And they're sort of combining geometry and algebra here. They want us to solve for x using the given information. Okay. So I'm going to start off my first statement with the stuff that I'm given. I'm given that QR is congruent to PQ. Right? I'm also given that RS is congruent to PQ. Okay? That's in my given information. I can also say that QR is equal to 2x plus 5, and RS is equal to 10 minus 3x. That is given information because it's on the picture. So all of that is by given information. Again, you can see different things for this. Sometimes people like to split all the given up, so you'd have 4 steps here. I'm combining everything they gave me, I wrote right away. That's my one given. So now I want something that lets me deal with the x's. So right now I don't have any relationship between Q and R, but they're both equal or both congruent to PQ. So I can say that QR is congruent to PQ, no, to RS, already know PQ, to RS, and that is transitive property. Okay, QR is equal to PQ, PQ is equal to RS, so QR and RS are congruent. That is transitive property. Then I want my variable stuff in here. So 2x plus 5 equals 10 minus 3x. That is substitution. The difference being that I'm not basing it on things being equal to something else. I'm replacing something that I know with something else. It's a slim difference between substitution and transitive, but that is the difference. Now I'm just doing algebra steps. Okay, so you could have some couple different things you could do here depending on how you want to solve it. I'm going to add 3x to both sides. So I have 5x plus 5 equals 10, which is addition because I'm adding the same thing to both sides. Then I'm going to subtract the 5. So I have 5x equals 5 based on subtraction. And then I'm going to divide by the other 5. I get x equals 1 based on division property. And again, all of these, I'm doing the same, everything to both sides. I'm adding to both sides, I'm subtracting from both sides, I'm dividing by both sides. Okay? So that is my proof for example 3. And that is the end of our 2.5 notes.